In the previous few lectures, we have discussed the concept of phase space. We have learnt about phase point, density of phase point, phase trajectory, and so many facts. Now, in today's lecture, we are going to see a very important concept, and this is regarding the division of phase space into phase cells, or you may say quantum states. Although you know that phase space and the phase space is actually a purely classical concept. But when you say quantum states, that is purely a quantum mechanical concept. But you will see that that in a semi-classical treatment, the idea of division of phase space into elementary cells, which is called phase cells, are just equivalent to quantum states. So when we deal the problem of classical statistics, then we talk in terms of the phase cells. But when we deal with the same problem in quantum statistics, the term quantum states is used instead of the phase cells. But first of all, definitely a question has been arised in your mind that what is the need to divide a phase space into phase cells? Why we divide it? Actually, when we will study the classical statistics or the quantum statistics, you will see that we deal with the law of distribution of particles, okay, both in classical and quantum statistics. The basic problem is how to distribute a particle into a phase space or in a quantum state, okay. Actually, to develop the laws of distribution of particles in phase space in case of classical statistics and in different quantum states in quantum statistics, we need the concept of division of a phase space into elementary volumes, and those elementary volumes are called phase cells. Actually, when we divide, or we, sorry, not divide, but when we distribute the particles among the different elementary cells of equal volume in phase space, that is actually called the micro state of the system, okay. And the purpose of dividing the phase space into phase cells is actually to study the distribution of particles of a dynamical system among these elementary cells, and so that we can develop the various relations in statistical mechanics, both in classical statistical mechanics and the quantum statistical mechanics. In fact, always you will see later on in the forthcoming videos that we always talk about the most probable macro state of the system when the system is in equilibrium, and then we develop the laws of distribution of particles, and for that purpose, for deriving such laws, we need to divide a phase space into phase cells. And when you talk in terms of quantum mechanics, that phase cell is simply called quantum states, okay. So I have told you that the phase space and the quantum states are two different concepts. As a the concept of phase space is used in classical mechanics, while the concept of quantum states is used in the quantum mechanics. But as I have told you, that we can establish a relation between them in quasi-classical case, which is very close to the classical mechanics. Okay, so I hope you have understand why we need to divide our phase space into the elementary cells of equal volumes, which are called phase cells. And when our system is quantum mechanical, then we simply call that phase cell quantum states. So this is just the two terms used for the same thing. So what is phase cells in statistical physics? That will be called quantum states in quantum statistical mechanics. Okay. Now, first of all, you have to know what should be the minimum size of the a phase cell. Okay, and to get the value of minimum size or minimum volume of a phase cell in phase space, first of all we will talk about the size of the phase cell, and after that we will see what should be the minimum value of the phase cell. So let us consider that we divide the phase space into elementary volume of equal elementary volume, you can say, and all those equal elementary volumes in which the volume in the phase space is divided, we call those elementary volumes simply phase cell. You can see this figure. Actually, in this figure, all these small squares, which we assume that they are actually those are not squares, but you can say they are three-dimensional volume element. But in this figure, since the figure has been drawn on a two-dimensional plane, so that appears like a square, but that is not a square, but all are actually the elementary volume, three-dimensional volume. And so you can say that all these squares, which appears like a square, represent a phase cell. Okay. Now you know that as this volume is in phase space, and you have learnt in the previous lecture that an elementary volume in phase space is just a product of two volumes. The first one is called volume of the element in the position space, and another is called volume of the element in momentum space. So what will be the volume of a phase cell? You can easily find on the basis of the concept which you have learned in the previous lecture. So let us consider that there is an elementary cell, and that elementary cell actually has position coordinate lying between x and x plus dx. Okay, it means if you consider that here is origin, then this the x coordinate of this point will be x, and that of this point will be x plus dx. So x coordinate of this elementary volume lies between x and x plus dx. Similarly, the y coordinate is between y and y plus dy, and z coordinate is between z and z plus dz. So you can say that there is a volume element in the position space having length, breadth and height equal to dx, dy and dz. So the volume of this volume element in position space will be what? If you denote that volume of the cell in position space by the symbol dv, then that dv is simply dx times dy times dz. Okay. Now we also consider that the momentum coordinates of this cell lies between px and px plus dpx, py and py plus dpy, pz and pz plus dpz. So the in momentum space, the volume of the same cell will be what? That will be equal to d tau, and that d tau is equal to dpx times dpy times dpz. So you can say that we have considered a volume element or a cell in the phase space whose volume in position space is dx dy dz, and the volume of the same cell is dpx dpy dpz in momentum space. And as you know that phase space is actually a superposition of the position space and the momentum space, and you have learnt in the previous lecture that a volume element in phase space is given by the product of the volume in position space and the momentum space. So if you consider that volume of this phase cell in the phase space is d gamma, then that d gamma will be what? That will be equal to dv times d tau, where you know this dv is dx dy dz, which is volume in the position space, and d tau, this is dpx dpy dpz, which is volume in momentum space. So the volume of the cell in phase space, which I have represented by the symbol this d gamma, this is also called hypervolume, that is equal to dx dy dz times dpx dpy dpz. Okay. Now let us consider that this is equal to h naught square. We consider it. Why this symbol h naught has been used, it will be clear to you after some time in this lecture. You will see. Actually, we will see later on that this h naught is recognized as Planck's constant h in quantum mechanics. Okay, but whenever you talk the problem in terms of classical mechanics, then you can't say that this h naught is Planck's constant, or it will be equal to Planck's constant. But when we will talk in terms of quantum statistics, then you will see that this h naught is nothing. This is simply the Planck's constant. Because you will see just now that the dimension of this h naught will be equal to the dimension of Planck's constant, that is the dimension of the product of energy and time, or work and time, or you can say action. Okay, we will see that this h naught has a dimension of action, and you know action means energy times energy multiplied by time, or work multiplied by time. You can check it. Let us see. As I have written this h naught cube instead of the product of dx dy dz and dpx dpy dpz. Since dx dy dz all are length, so h naught, the dimension of h naught, you can say this will be equal to length cube times momentum cube. dpx dpy dpz has dimension of momentum. So the dimension of h naught cube, you can say that will be equal to dimension of length cube times momentum cube. Okay. So the dimension of h naught will be what? That will be simply equal to dimension of length times dimension of momentum. Okay. Now, as you know that force F in accordance with Newton's second law of motion, this is dp dt, and so dp is what? dp is f dt. So regarding the momentum, you can say that instead of momentum, we can write force times time, force into time. So instead of momentum, I have written here force into time. Okay. Again, you know that work is just the product of force and displacement means length. So the product of this length and force will have a dimension of work. So instead of length into force, you may write work. So the dimension of h naught, you can say this is simply equal to work into time. And as you know, the dimension of work is same as that of the energy. Both have same unit and same dimension. So instead of work, you may write energy. Okay. So and what is the dimension of h naught? dimension of H naught will be simply equal to dimension of energy and time. And you may write it like this. You know that dimension of energy is ml2 T inverse 2 times T. So this will be simply equal to ml2 T inverse. ml2 T inverse. Or you can say joule times second. Okay. So you can see that dimension of this constant H naught which we have assumed is just equal to what? This is just the dimension of action, that is the dimension of product of energy and time. Okay. And now our aim is to find the minimum size of this phase cell. You have seen that this d gamma, we have assumed that this is equal to H naught cube. So what will be the minimum value of this H naught cube? Now we are going to find it. As you know that in classical mechanics, there is no restriction on measuring the position and momentum of a particle simultaneously. There is no restriction. When you say that there is no restriction on measuring the position and momentum of a particle simultaneously in classical mechanics, what does it mean? It means we can measure the position of a particle and the momentum of a particle simultaneously with any accuracy. It means we can measure these two quantities simultaneously without any error, without any uncertainty. We can calculate the exact value of position and momentum in accordance with classical mechanics. Okay? And in classical mechanics, you know that a particle is treated just like a dimension. So when you will talk this phase cell in terms of the classical mechanics, the size of this cell may be decreased, it may be continuously decreased, and finally it will turn into a particle and its volume will be tend to zero. So simply you can say that in classical mechanics, the minimum size of the phase cell may be zero. It will just convert into a particle, and a particle is treated in classical mechanics just like a geometrical point having no dimension. So in classical statistical mechanics, you can say that the volume of the phase cell may tends towards zero. So you can see I have written here, because I have mentioned it here that a particle can therefore be represented by a geometrical point in phase space, and so H naught cube can be made as small as we please. Okay, and so we can say in classical mechanics this H naught cube may tend to zero, and so that this volume of this phase cell may tends to zero in classical mechanics. But when you talk about the quantum system, or when you deal with the same problem in terms of quantum mechanics, what will happen? Actually, our nature behaves not like not classically, but the behavior of nature is governed actually by the quantum mechanics. Okay. And in quantum mechanics, you know, according to Heisenberg uncertainty principle, the measurement of the position and the momentum are restricted. You can't measure position and momentum of a particle simultaneously with any accuracy. Whenever there will be a simultaneous measurement of position and momentum in accordance with Heisenberg uncertainty principle, definitely there will be some uncertainties, there will be some error in measuring the position and the momentum of the particle. And what will be the product of those uncertainties, those errors, that has been stated in the Heisenberg uncertainty principle. So according to Heisenberg uncertainty principle, if you say that in measuring the position the uncertainty is dx, and in measuring the conjugate momentum, it means when you talk about the position coordinate x, then the conjugate momentum is px. Okay, when you say the position coordinate is y, then the conjugate momentum is py, and for the position coordinate z, the conjugate momentum is pz. And according to Heisenberg uncertainty principle, the product of the uncertainty in position and its conjugate momentum, that is dx times dpx, this is never less than Planck's constant h. It is always greater or equal to h. And similarly, the product of the uncertainties in measuring the position coordinate y and its conjugate momentum, that is dy times dpy, it is also equal or greater than h. Okay, and similarly you can say that the product of the uncertainties in measuring the z coordinate and its conjugate momentum pz, which is dz into dpz, that is also greater or equal to h. Okay, so when you will find the volume of a phase cell in accordance with the quantum mechanics, what will be the result? Now let us see that the volume of the phase cell d gamma, you know, it is given by dx times dy times dz times dpx dpy dpz. And I have written that expression here by arranging the terms. I have written that d gamma is equal to dx times dpx times dy dpy times dz dpz. But as you know, according to Heisenberg uncertainty principle, the product of dx and dpx, this is greater or equal to h. This product dy and dpy, this is also greater or equal to h, and this product dz and dpz is also greater or equal to h. So this d gamma, in accordance with the Heisenberg uncertainty principle, this must be greater or equal to h cube. Okay, so d gamma in general, that is volume of a phase cell in accordance with quantum mechanics, must be greater or equal to h cube. It means the volume of the phase cell in accordance with quantum mechanics, it will be never less than h cube, where h is Planck's constant. Okay, so what will be the minimum value of a phase cell? For getting the minimum value, we will take the sign of equality. So you can say that the minimum value of a phase cell in accordance with quantum mechanics, that will be d gamma minimum equal to h cube. Okay, so what is the difference? You can mark the difference in the classical treatment and the quantum mechanical treatment. In accordance with classical mechanics, the volume of a phase cell may tends to zero, but according to quantum mechanics, the volume of a phase cell cannot be less than h cube. Okay, so the minimum value of the volume of a phase cell in accordance with quantum mechanics is equal to h cube. But now see this fact on practical basis. You know, the value of Planck's constant h is equal to 6.63 times 10 to the power minus 34 joule second. Okay, so what will be the value of h cube? When you will find the value of h cube, you will get this is 2.91 into 10 to the power minus 100 joule cube second cube. You can imagine what is the actual effective value of this number 2.91 into 10 to the power minus 100. You can easily say that this number is very close to 0. This is very, although this is not 0, but as 10 as the 10 contains a power of minus 100, it means this is a number which is almost equal to 0. So you can say that the quantum mechanical result and the classical result are not very different, because this number 2.91 into 10 to the power minus 100 is practically almost 0. So the classical result, which according to which the minimum size of a phase cell is just 0, and according to quantum mechanics the minimum size of a phase cell is in fact h cube. But these two statements or these two values are not very different practically. Practically or effectively, this number can be taken as 0. Okay, so you can say that this classical result and this quantum mechanical result are not very different. Okay, now as we have considered the system in consideration, you have considered that there are 3 position coordinates x, y, z, and there are 3 momentum coordinates px, py, pz. You have considered to describe a system. As you know, the number of independent variables to describe a system is called degree of freedom of this, is called degree of freedom of the system. Okay, so here, as this system can make its motion either along x-axis or y-axis or z-axis, so actually this system has 3 degrees of freedom. Okay, and the number of independent variables, both position and momentum coordinates, that represents the dimension of the space. So you know our space which we are talking about is actually here 6 dimensional, because we need 3 position coordinate and 3 momentum coordinate to describe this space, to describe the state of a system in this space. So in general, you know that if f is the degree of freedom of a system, then we say that our phase space is 2f dimensional. You have learnt. If f is, because I have actually explained in the previous lecture that the dimension of a phase space depends on the degree of freedom of the system. If f is the degree of freedom of the system, then 2f is called dimension of the space. Okay, here the dimension of the phase space about which we are talking is 6. So you can say that if f is the degree of freedom of our system, then this 2f in this present example is equal to 6. Okay, and so f is equal to 3, it means the degree of freedom is 3. And as you can see that the minimum size or minimum volume of phase space is equal to h cube, you can say that this power 3 is nothing. This is simply the degree of freedom of our system. So in general, you can say that the minimum volume of a phase cell or the minimum volume of a quantum state, in a state of phase cell, now you can use the term quantum state. Okay, so minimum volume of a quantum state is equal to what? This is h to the power f, you can say. So if the degree of freedom of a system will be, let us say, 5, then what will be the minimum size of the phase cell? That will be h to the power 5. If the degree of freedom of a phase space, degree of freedom of a system in phase space is, let us say, f equal to 10, then what will be the minimum size of the phase cell? That will be h to the power 10. So actually the minimum size of a phase cell or the minimum size of minimum volume of a quantum state depends on the degree of freedom of our system. Okay, degree of freedom, and you can see this result independently. Here actually I have derived this result that d gamma minimum equal to h to the power f from the example mentioned above. But in general, if you consider that our phase space is 2f dimensional, and if the phase space is 2f dimensional, then you know we will need f position coordinate and f momentum coordinate to describe the state of a system in that phase space. So, in general, if we consider that our phase space is 2f dimensional, then the position coordinates needed to describe the position of the system in that phase space are represented like this. This is q1, q2, so on, qm. It means the number of position coordinates will be f. And similarly, we also need the momentum coordinates whose number is also f. So momentum coordinates are p1, p2, so on, pf. So in this phase space, what will be the volume of the phase cell? As you know, the volume of phase cell is simply equal to volume in position space times volume in momentum space. And volume in position space will be what? That will be dq1 into dq2, so on, dqf times dp1, dp2, so on, dpf. Okay. Now arrange the terms in RHS in this manner. You can write dq1 dp1 times dq2 dp2, so on, dqf dpf. As you know that if q is the position coordinate, then corresponding to, sorry, if q1 is the position coordinate, its conjugate momentum is p1. Okay, and for the position coordinate q2, the conjugate momentum is p2, and so on. So, according to Heisenberg uncertainty principle, again the product of this dq1 dp1 will be greater or equal to in fact h cube. So you may use the term you may use the sign of greater or equal to here. Greater or equal to. See here. This is greater or equal to this much. Okay. Greater or equal to. In fact, every term inside this bracket will be greater or equal to h. So this product will be greater or equal to h into h up to f times f term up to f times, yes, and that will be greater or equal to h to the power f. Okay, and in brief you can write this expression like this. This is this d gamma will be greater or equal to pi I to f dqi dpi. Okay, and this will be actually greater or equal to, again you can say, h to the power f. Greater or equal to h to the power f. Okay, and so if you talk about the minimum value of this d gamma minimum, then this d gamma minimum, this will be equal to h to the power f. Okay, so the minimum size or minimum volume of a phase space or a quantum state, actually we can use the term quantum state instead of phase cell, instead of phase cell. Okay, that will be equal to h to the power f, where h is Planck's constant and f is the degree of freedom of the system in that phase space. Okay, so you can say that the total volume of the phase cells in the phase space, and the total volume in phase space of the phase cells phase cells. Here actually this total volume has been written for the minimum total volume. You can say hence the minimum total volume. I am not now writing the sign minimum, but this delta gamma represents the minimum total volume in phase space of the phase cell. That will be simply equal to integral of this much. Okay, when you will integrate this, you will get actually the total volume of the phase cells in the phase space. Now you have learnt that the volume of minimum volume of one phase cell, minimum volume of uh, minimum volume of one phase cell is h to the power f, and total volume of all phase cells is equal to integral of this. Okay, so if you want to find the number of phase cells in the phase space, how you can find? This is the total volume of all phase cells, and the volume of one phase cell is h to the power f. Okay, so when you will divide the total volume of all phase cells by the volume of one phase cell, you will get the total number of phase cells or total number of quantum states in the phase space. So you can see here the number of quantum states or the number of phase cells. If we denote it by the symbol g, that g will be equal to this much. This is integral pi I 1 to f dq at dpi and divided by h to the power f. Actually this numerator denotes the total volume of the phase cells, and h to the power f represent the volume of one phase cell. So when we will divide the total volume of phase cells by volume of one phase cell, we will get the number of phase cells or the number of quantum states. Actually this result finds various application when you will deal with the problem of distribution of particle among the different phase cells while discussing the problem of classical statistics, that is Maxwell-Boltzmann distribution, or the quantum statistics, that is when we will talk about the Bose-Einstein statistics and the Fermi-Dirac statistics. You will see that to get the laws of distribution of particles, we will need to find this number of phase cells in the phase space or the number of quantum states when we will talk in terms of quantum statistics. So, and here which I have mentioned earlier, that why there is a need to divide the phase space into phase cell, I have mentioned it here, but I have explained this fact in the very beginning of this lecture. So I am just giving a reading here. You can see the purpose of dividing the phase space into phase cells or quantum states is to study the distribution of particles of a dynamical system among these cells or quantum states, and hence to develop various relations in statistical thermodynamics for the most probable macro state of the system when the system is in equilibrium. Actually distribution of particle among these phase cells or quantum states is called microstate. Okay, and in terms of that microstate we obtain the most probability for the most probable macrostate, and then we will develop the laws of distribution of particles. So I hope you have understand the idea of division of a phase cell, division of a phase space into phase cells or in quantum states. Actually, this basic concept is needed for the understanding of the different concept regarding the distribution of particles, as I have told you earlier. And in next lecture again we will see a very important basic fact, and after that we will start to deal with the first concept of classical statistical mechanics, that will be Maxwell-Boltzmann distribution law and the ideal or perfect gas in classical statistics. Okay, so thank you very much.